In the fourth lecture, we will cover some statistical concepts related to multiple random variables, such as the joint, marginal, and the conditional distributions, covariance, and the correlation. The concepts further extend to the random sample, where we have independent and identically distributed random variables. Also, we will learn the estimator, an important concept in statistical inference. In Lecture 1, we introduced joint probability when we have more than one event. We know an event is a subset of the sample space. When we enlarge the event to the whole sample space, the concept of the joint probability of events is widened to the joint distribution of random variables. When we have more than one random variable, we use the subscripts in the distribution function to label the related random variables. The joint cumulative distribution of x and y is capital F with subscript xy, which is the probability of random variable x equal to or smaller than value x, and the random variable y equal to or smaller than value y. The discrete probability distribution is the probability mass function p with subscript xy, and the continuous probability distribution is the probability density function f with subscript xy, which is a derivative of the joint cumulative distribution function. A marginal distribution gives the probability of the variables in the subset without reference to the discarded variables. For example, marginal probability mass function p with subscript x is the sum of all y values on the joint probability mass function p with subscript xy. Graphically, it means we push the joint function to axis x and discard axis y. The conditional distribution of y given x is the probability distribution of the random variable y given the random variable x equal to x. The sample space of the conditional distribution is limited to a slice x to x of the original two-dimensional space. It is the slice x equal to x of the joint probability density function fxy, and standardize it with the corresponding marginal distribution fx. We learned the event independence in Lecture 1. Similarly, we may extend the concept to random variables. If two random variables x and y are independent, then their joint function is the product of their marginal functions. Also, from the definition above, if they are independent, the conditional distributions are equal to their corresponding marginal distributions. Roll a dice 5 times, and what is the chance of 2 ones and 2 sixes? If we flip a coin 5 times, we have a binomial distribution of n equal to 5, because there are only 2 outcomes in each trial. When there are more than 2 outcomes for each trial, the distribution is multinomial, as a generalization of the binomial distribution. The multinomial distribution is a joint distribution with this probability density function. Here, n equal to 5. Although the sample space is 1 to 6, it may be regrouped into 3 groups for this problem: 1, 6, and 2 to 5. Thus, k is equal to 3 instead of 6. Correspondingly, P1 is equal to P2 is equal to 1 over 6, and P3 is 2 over 3 for the three groups. Using the probability mass function, we have the chance of 2 1s and 2 6 is about 1.5%. This example helps us to understand the joint distribution of discrete random variables. Next, let's find the joint distribution of two independent random variables with normal distributions. As we learned, the marginal probability density functions of random variables with normal distributions are written here as fy1 and fy2. Since y1 and y2 are independent, we know the joint distribution fy1, y2 is fy1 multiply fy2, and this is the joint probability density function, known as the bivariate normal distribution. However, if the two random variables are dependent, then the joint distribution is much more complex. If the two random variables are dependent, then they may have linear or nonlinear relationship between the random variables. Both covariance and correlation measure the linear relationship between random variables. Covariance between random variables x and y is defined as the expectation of x minus mu x, y minus mu y. It can be simplified as the expectation of xy minus mu x mu y. From definition, the covariance between x and itself is the variance of random variable x. When we have multiple random variables, it is convenient to use the matrix form in many cases. A covariance or variance-covariance matrix is a square matrix giving the covariance between the random variables. This is a 2 by 2 covariance matrix between two random variables x and y. Since x and y in covariance is interchangeable, the matrix is symmetric. If x and y are independent, then the matrix is a diagonal matrix, since the covariance between x and y is 0. Here are some basic properties, and they are direct results from the definition of covariance. Based on the properties, we may find the variance of x plus y is this, since the variance is the covariance between the random variable and itself. Correlation between random variables x and y is defined as their covariance divided by sigma x, sigma y, where sigma x and sigma y are the standard deviations of x and y. Based on their definitions, covariance has the same unit as xy, and the correlation is dimensionless and ranges from -1 to 1. If the correlation is 0, then random variables x and y are uncorrelated. If the correlation is -1, then x and y has a perfectly negative linear relationship. If the correlation is 1, then x and y has a perfectly positive linear relationship. If random variables x and y are independent, then the correlation is 0, because the two variables are not related. On the other hand, if x and y are uncorrelated, it only means they are not linearly related. They may not be independent. A collection of random variables y1 to yn is a random sample of size n if the random variables are independent and identically distributed as IID. For example, we toss a coin 3 times. The tosses are independent, and each tossing as a random variable has a Bernoulli distribution. So it is a random sample of size 3. Also, if we randomly select 1,000 adults with replacement from all adults and measure their heights, then it is a random sample of size 1,000. Selection with replacement means the selected adult will be placed back into the population after each selection. Thus, it is possible that the same adult is selected multiple times in a random sample. Now, let's look at the joint cumulative distribution function and the joint probability density function of a random sample of size n. Since n random variables are mutually independent, the joint distributions are the product of their marginal probabilities. For example, we may derive the joint distribution of a random sample of size n with identical exponential distributions. Since the random variables are independent and identically distributed, we only have one parameter lambda for all marginal distributions. Thus, the joint probability density function is lambda to the power of n multiply the exponential of minus lambda sum of yi. The joint distribution of a random sample of size n with identical normal distributions may be written as this. Here, yi minus mu divided by sigma is the z-score, which follows the standard normal distribution. The joint distribution may show the likelihood for all outcomes in a random sample. However, in many cases, the joint distribution is not analytic. Fortunately, we usually don't need to use the joint distribution of the sample thanks to the sampling distribution, which we introduce in the next lecture. Previously, we introduced some important measures of the random variable, such as mean and variance. In this slide, we will show how we may make inference on these measures. For example, we have a population of size capital N and a random sample from the population with a sample size n. The population mean mu is a parameter and the sample mean y bar is a statistic. The population variance is sigma square, also a parameter, and the sample variance S square is a statistic. Let us not dig into the formula of the sample variance now. We will do it later. We need to introduce an important concept here, estimator. Estimator is a statistic used to infer the parameter. So here, sample mean y bar is an estimator of the population mean mu, and the sample variance S square is an estimator of the population variance sigma square. If the estimated parameter is theta, we may write this estimator as theta hat. The bias of an estimator is E theta hat minus theta, the distance between the expected value of the estimator and the parameter. Now, how to understand the expected value of the estimator? We know the estimator is a statistic, and it is from a sample. For example, the sample mean is an estimator. One sample gives one sample mean y bar. If we have other samples from the same population, then we may have many sample means. So the sample mean is also a random variable. Thus, we may have the expectation of an estimator. The bias is the difference between the expected value and the true value. In this case, the difference between the expected value of the sample mean and the population mean. The estimator is unbiased if and only if E theta hat equals to theta. For example, the sample mean is an unbiased estimator of the population mean. Here, we may put the expectation inside the summation due to the linearity of the expectation. Also, we may define the variance of an estimator. It is the expected value of the squared difference between the estimator and its expected value. The mean squared error of an estimator theta hat is the expectation of the squared difference between the estimator and the parameter theta. Thus, mean squared error is an important performance measure of the estimator. We may derive MSE of theta hat is the sum of its bias square and its variance based on its definition. Thus, when the estimator is unbiased, such as the sample mean, then the mean squared error is equal to the variance of the estimator. In summary, we studied joint, marginal, and conditional distributions, covariance and correlation, random sample, and estimator in this lecture. When we have more than one random variable, we have the joint distribution that may be described by the joint cumulative distribution function or the joint probability distribution function. The marginal distribution gives the probability of the variables in the subset without reference to the discarded variables. The conditional distribution is the probability distribution of the variables given condition on other variables. If two random variables x and y are independent, then their joint distribution is the product of their marginal distributions, or equivalently, the conditional probabilities are equal to their marginal probabilities. Covariance and correlation both measure the linear relationship between random variables. Covariance between random variables x and y is defined as the expectation of x minus mu x, y minus mu y, while correlation between x and y is defined as their covariance divided by sigma x, sigma y. Correlation is dimensionless and ranges between -1 to 1. A random sample of size n is a collection of independent and identically distributed random variables y1, y2, yn. Because n random variables are mutually independent, the joint distribution of a random sample are the product of their marginal probabilities. Estimator is a statistic used to infer the parameter. For example, sample mean is an estimator of mu, and sample variance, S squared, is an estimator of the population variance. Bias of an estimator is the difference between the expectation of the estimator and the parameter. Variance of an estimator is the expectation of the squared difference between the estimator and its expectation. and the mean squared error is the expectation of the squared difference between the estimator and the parameter.